Hello everyone. Today we are going to discuss field due to infinite line charge or cylindrically symmetric charge distribution. Clear? So let us consider infinite thin rod, okay? So we have infinite thin rod, okay? And it is uniform in diameter, okay? So let the rod contains positive charge, okay? So we have this. Clear? Now let lambda be the charge density of the rod. So this is rod, clear, having infinite length and is thin and is containing charge, that is positive charge, distributed uniformly throughout its length. So we have this. Now, as mentioned, we have cylindrically symmetric charge distribution. Clear? Since the rod is thin cylinder, so in order to apply Gauss law, we must select or choose a Gaussian surface, and we take cylindrical Gaussian surface in this case. Clear? So let us draw a cylindrical Gaussian surface, okay, which is coaxial with the rod. So this is cylindrical Gaussian surface of radius r, okay, radius r and length L. Length of the cylinder is L and coaxial with the rod. So we have this. Now we know in order to apply Gauss law, the surface must be closed. So let the cylinder be closed at both the end cap. So we have this. We have a plain closed end cap, okay, and this is plain, okay. Now let us consider point P on the outer surface, that is curved surface of the cylinder, okay. So we are taking point P on the outer curved surface of the cylinder, and let us take a small elementary area, okay. This is a small elementary area on the outer region outer region of the Gaussian surface having area dA in magnitude. So we have this. Clear? As I said earlier, we want to find electric field at this point, that is at point P, due to charge within this cylindrical Gaussian surface. Clear? So I'm writing over here. We want to find electric field at point P, okay, which is at distance r from the rod, okay, point P, due to charge inside the Gaussian surface. That means we have to find total electric field or resultant electric field due to all charges within this cylindrical Gaussian surface. Clear? And we have point P on the outer region of the Gaussian surface at the curved part. Okay, so we need to know this. Now let me draw this figure, okay, over here in order to understand in more detail. Okay, so this is the thin rod, okay, which is infinitely long. It is the same, okay, this is the same, it is the same figure, okay, and the rod contains positive charge distributed uniformly throughout its length. Okay, so this is linear charge density, so we need to note this. Now we have a cylindrical Gaussian surface. Okay, now let us consider a point. Okay, I'm taking a point, this point, and we want to find total electric field at this point, that is P, due to charges inside the Gaussian surface. So as I said earlier, we take a small elementary area. Okay, we take a small elementary area. Yeah, and its magnitude is dA. So we have this. Now point P is at distance small r from the rod. Now let us take a charge element, okay, Q dash. So we can think in this way. Okay, let's understand with reference to the axis. Okay, so we take vertical direction as positive y and vertically downward direction as negative y. Okay, so we have this. So what we find in this figure is that Q, this is total charge inside the Gaussian surface, and Q dash is charge element on, let's say, positive y axis. Clear? and let the charge element q dash be at distance small a from this point. Okay, so let's call this point as O. This is O. Okay, now we always know electric field or electric flux due to positive charge always directs outward, so that electric field due to this charge element at point P, okay, is E1, okay, and I'm writing in vector form. So we have this. Clear? Now, by symmetry, okay, what we find by symmetry, okay, for every charge element, or let me write in this way, for charge element q dash on plus y axis, we find charge element, okay, q dash on negative y axis. Okay, so we find by symmetry charge element q dash at same height, okay, below point O. Clear? Now this charge element will give electric field E2 in outward direction. Clear? So we have this. Now what we do, and this is closed, okay, the cylinder is closed at both the end caps. Now let us resolve electric field E1 and E2, okay, so in horizontal and vertical direction. So E2 along this direction is E2 cos theta, and along this direction is E2 sin theta, and E1 along this direction is E1 cos theta, and along this direction is E1 sin theta. Now if we look into this figure, okay, or into this triangle, we know this, okay, this height is A, this is R, and this distance is under root, this is R, okay, under root R is square plus A square. So this distance is under root R is square plus A square. In same way, this distance, okay, this distance is under root R square plus A square. Now what we find, magnitude of E1, okay, so this equals 1 by 4 pi epsilon naught q dash divided by this distance, okay, this distance, and this distance is under root R square plus A square whole power 2, 1 by 4 pi epsilon naught q divided by R square. This is the general formula, okay, for electric field R square. Okay, so we have this. Now, in same way, magnitude of E2 is 1 by 4 pi epsilon naught, okay, due to this Q dash divided by square of this distance, okay. So we have this under root r square plus a square whole divided by 2. So what we get, magnitude of E1 equals magnitude of E2. So we can draw this conclusion, okay. One, E1 sine theta and E2 sine theta cancels out. They contribute nothing in order to find total electric field at point P. Next, E1 cos theta and E2 cos theta, they add up to give total electric field at point P. So the radial component, okay, we can see E2 cos theta and E1 cos theta, they are acting radially outward. So what conclusion can we draw is that for every pair of charged element, okay, we find the sign component, okay, cancels out, and the cos component, okay, or this component, they add up to give the total electric field. So what we find, if you look into this figure, E1 sine theta and E2 sine theta, they are parallel to the curved surface, and the component which is parallel to the curved surface, they cancels out. So directly looking into this figure, we can tell that there is no flux passing through the curved surface, sorry, through the end cap. There is no flux passing through the end cap because the component parallel to the curved surface, okay, the component parallel to the curved surface, okay, cancels out. So there is no flux through the end cap, whereas the radial component, they add to give total electric field, okay. So we use this concept in this figure, okay. So we are going to find the total electric field at point P, that is resultant electric field at point P due to charge inside the Gaussian surface. Clear? So I'm erasing this, okay. Now, we apply Gauss law, okay, and we find there are two end cap which is plane, and there is a curved surface on this cylindrical Gaussian surface. So we apply Gauss law, and from Gauss law, okay, we can write total electric flux this equals surface integral of electric field throughout the closed path or closed surface equals Q by epsilon naught. So this is charge, okay, this is charge inside the Gaussian surface. Clear? So we have this. So let's call it equation 1. Now we can write in this way, okay, total flux, okay, this equals flux through the curved surface of the cylinder plus flux through end caps, and there are 2 end caps. So let us find this, okay. So this is equation 2. Clear? Now to find this, what is this? This is flux through curved surface of the cylinder. Now we know we have this. Now, as I said earlier, electric field on the curved surface, okay, or at point P is directed radially outward. Yeah? And this is the resultant electric field at point P due to charges within the cylindrical Gaussian surface. Okay, so this is to be noted. Okay, now what we do is that we know area vector can be expressed in this way. So this is unit normal, okay, drawn on the area, and it gives the direction of vector area. Clear? So on the curved surface, okay, we find electric field and area vector, okay. Electric field and area vector, they are parallel to each other. Clear? Because by symmetry, or from the condition of symmetry, okay, from condition of symmetry, is parallel to the area vector. Clear? We have electric field parallel to area vector on the surface, okay, or on the surface chosen, and we have cylindrical Gaussian surface. So on the curved surface of the cylinder, electric field is parallel to the area vector. And next, electric field is constant, okay, on the surface. So electric field is constant. So if electric field is constant, then we can take electric field out of the integral. So we can determine electric field. And third, for this integral to be 0, okay, for this integral to be 0, electric field to apply these conditions of symmetry for infinite line charge. Clear? Now, as I said earlier, at each point on this cylindrical Gaussian surface, electric field is constant in magnitude, and on the surface, clear, electric field and area vector, they are parallel to each other. So we can write in this way, E, and we have this, and this integral gives us total area of the curved surface. of the cylinder. Clear? And this is 2 pi r, that is radius of the cylinder, and we have length, okay, that is length of the cylinder. So we can write flux through the curved surface equals E times twice pi RL. So we have this. So let's call it equation 3. So as we have discussed earlier, okay, we find electric field at point P due to charge inside the Gaussian surface acting radially outward. Here we find this. And to find flux through end caps, okay, so flux through end cap. So this is flux through end cap. So what we do for end caps, okay, we have this. Now let us choose a small elementary area, okay, on the upper end cap, okay, this is upper end cap, and this is lower end cap, okay. So this end cap is facing up. So let us draw a unit normal, okay, let us draw a unit normal facing up, and it gives the direction of area vector which acts in upward direction. And as we have discussed, electric field is directed radially outward. So at the end cap, we find angle between electric field and area vector is 90 degree. So same way, so we have a small elementary area, okay, on the lower end cap, and this end cap is facing down, so that the unit normal is acting downward, or area vector is acting downward. And since electric field is directed radially outward, okay, so that for both the end cap, the angle between area vector and electric field is 90 degree. So for both, so I'm writing for both end caps, okay, we get this cos 90 degree, and this gives us 0. So it means that no electric lines or electric flux crosses through the end cap, and we have discussed this in the previous diagram also, okay. So we are getting this. So now we can write in this way, okay, through end caps. So flux through end caps, okay, through both end caps, this is 0. Now what we get from 2, 3 and 4, okay, total electric flux, this is, so this is E times twice pi RL. So we can write in this way, E times twice pi RL, and this is 0, okay. So I'm writing directly, okay. So this is the total electric flux through the cylindrical Gaussian surface. Now let us call it equation 5, okay. Sorry. Now from 1 and 5, okay? Now from 1 and 5, we find, okay, this is E times twice pi RL, and this equals, we have this, okay? We are using this, Q divided by epsilon naught, and this is charge inside the cylindrical Gaussian surface. So what we do, we write E equals Q by 2 pi epsilon naught, and we have R, radius of cylindrical Gaussian surface, and we have L, length of cylindrical Gaussian surface. Now we know linear charge density, okay? This is linear charge density of the rod, okay? Of the rod, and this equals charge per unit length. So we can write E equals lambda by 2 pi epsilon naught R. So this is electric field at point P, okay, due to infinite line charge.